Okay, this video will deal with homework problems from chapter 2, and I'm going to work out problems 1. Well, we'll start with problem 1. I don't know if I'm going to do all 5, 1 through 5, but we're gonna work on problems from chapter 2. Now, this is about hypothesis testing. Remember, hypothesis testing is a key component to what we're going to do moving forward in this class. And so we want my Zoom studio whiteboard is a little dusty. Haven't been up here for a few months. We want to understand these questions. So what we're working on here is hypothesis testing. Right? Hypothesis testing. The idea here is that we have a single observation. Based on a sample. That's it. We take one observation based on a sample, right? We ran our experiment one time. We want to know, can we formulate a conclusion about the population? Can this lead to a conclusion about the population? And the way we're going to conduct this hypothesis test is we're going to write our null hypothesis, right? Our null hypothesis will be the no impact hypothesis, no relationship. And our alternative hypothesis will be that the word we'll use here is independent, right? Our variables are independent of each other. Here we're going to say there is a relationship. And our conclusion, right? Our conclusion based on our statistical approach is going to be one of two outcomes. We're either going to reject H naught in favor of HA, or we're going to fail to reject H naught. As we go through these problems, pay attention to the fact that the conclusions we formulate are always one of these two. We're going to reject H naught, the idea that their variables are independent, that there's no relationship, that one has no impact on the other, in favor of there is a relationship, right? There is a relationship. They're not independent. That is one possible outcome. The other possible outcome is going to be that we cannot reject the claim that they're independent. We cannot prove that there is a relationship between the variables. Okay, those are our two outcomes. And the way we're going to come to this conclusion, right, is we're going to look at our sample. We're going to see what result our sample returns. And we're going to ask ourselves in the beginning, in this part of the video or in this part of the book, we're going to ask ourselves, is this a rare event or is this a non-rare event, an event that I can expect to happen often? If it's a rare event, then we're going to say, okay, that tells me, right? That tells me that what I've witnessed would not have happened if H naught were true. Right? Write that down. What I witnessed would not have happened if H naught were true. That's a rare event. A rare event, again, is something that would not have happened. I would not have expected to see this occur if H naught is true. Now, I asked you to read sections 2.2 and 2.3 at least once, if not twice, over the course of between our last class meeting and our next class meeting. I hope you've done that before you watch this video. All right, so let's start with problem number 1. Like most statistics problems, right, there's a lot of reading and a lot of information to digest. Problem 1 says side effects of Avandia, part 1. Okay, so we're looking for side effects from a drug here. So we have this drug, rosgilazone is the active ingredient in the controversial type 2 diabetes medication, Avandia, and has been linked to an increased risk of serious cardiovascular problems such as stroke, heart failure, and death. A common alternative treatment is another drug that starts, we're going to go with drug R and drug P, right? That we don't have to worry about these big words. The active ingredient in a diabetes medication called Actos. In a nationwide retrospective observational study of 227,571 Medicare beneficiaries aged 65 years or older. Now, remember, this says retrospective observational study. What does that mean? We went back and looked at what happened to these individuals. We know some of them took the R drug, which could cause problems. We're not sure if it does. And some of them took the P drug, which we know doesn't cause problems. Right? So we're not doing an experiment here. We're not giving these drugs to two groups of people. We think one drug causes issues. That would be unethical for us to give that drug to human beings. So we're going backwards in time and we're looking at what happened when they took the drugs. That's why they say it's a retrospective study. It was found that 2,593 of the 67,593 patients using the suspected troublemaking drug and 5,386 and 159,978 using the other drug had serious problems. So both drugs had individuals who had problems. The data are summarized in the contingencies table below. So they give us a table, right? And so we have our R drug and we have our P drug. And we have, yes, they had problems. No, they did not have problems. And we said there were 2,593 of those, and 5,386 of this. Now, we had a total of 67,593 individuals taking this drug here, and we had 159,978 individuals taking this drug here. It says in the problem number 1 is determine if each of the following statements is true or false. If false, explain why. Be careful, the reasoning may be wrong even if the statement's conclusion is correct. We're supposed to see the logic behind the idea of, is this drug more harmful than this drug, right? That's what they're asking us to consider here. So statement A says, since more patients on this drug, right, 5,386, had problems, yes, they had problems, then the number of patients on this drug, we can conclude that the rate of cardiovascular problems for people on the drug that started with a P is higher. I mean, that's a bigger number. That's a bigger number than this number. So they're saying, well, 5,300 people, almost 5,400 people had problems on this drug. Only 2,600 people had problems on this drug. Clearly, this drug is more risk-oriented than this drug. And they want us to tell them whether we think that's true or false, right? Well, look over here. We had 70,000 people if we round up on this drug. We had 160,000 people on this drug. Given these people are over the age of 65, we know they're going to have cardiovascular problems, right? Well, you have cardiovascular problems when you're over the age of 65. That's just part of life. So we knew that there was going to be something in the yes category here. Just counting the number of people in each category, though, that's not logically sound because we don't have the same number of individuals over here being subjected to each of these drugs. So statement A saying this is a higher number, so this drug's worse, that's false, right? That's false. And they want us to say why. And the why is we should consider percentages, right? I mean, that would really tell us whether or not counts aren't good here, right? Counts are not good because we didn't have the same number of people taking each drug. In fact, we had a vastly larger number of people taking this drug, so we would have expected that to be high. What about part B? The data suggests, okay, now that's a big word. Notice they only said suggest. They didn't say prove. They didn't say substantiate. Suggest that the diabetic patients who are taking this drug, the R drug, are more likely to have cardiovascular problems since the rate of increase. Okay? So now they work out for us here the percentages. They tell us this divided by this, right? They tell us this percentage is 0.038. And they tell us this percentage right here is 0.034, right? So R, we had cardiovascular problems in 3.8% of our patients versus the drug that started with a P, we had cardiovascular problems in only 3.4% of our patients. So they say in part B, because this rate is higher than this rate, that suggests, keyword here, suggests that this drug is more risk oriented, has a higher probability of causing problems in our patients. That statement is true, right? That statement is true. There's nothing about that statement that's false, and they don't say prove or substantiate. They say suggest. So that statement is true. What about part C? The fact that the rate of incidence is higher here than it is here proves, see, now that's a big word, proves. We know proves requires some kind of strong statistical substantiation. Proves that the R drug causes serious cardiovascular problems. That statement is false, right? False. False. It doesn't prove anything. We have an association here, right? We have an association here. We can say it's associated with a higher rate, but we know association does not prove causation. To get causation, we need to run an experiment. This is not an experiment, it's an observational study. What about part D? Based on the information provided so far, see, already we're hedging our bets there, so far, we cannot tell if the difference between the rates of indices is due to a relationship between the two variables, or maybe just to chance. You know, we have not proven that this growth is related to these drugs. We haven't proven that. It could be just this is what happened with our sample. So that statement is true. And that statement is true. Now, when we take a test or we take a quiz, these are the kind of questions we're going to be given. We are going to have to be able to reason out the validity or the lack thereof for statements such as this on a statement or a quiz, or on a test or a quiz. All right, so that's question number 1. go ahead and erase this down here. We'll keep this background information up above. Question 2, heart transplants. It says in exercise 1.5, we were introduced to the Stanford heart transplant study of 34 patients in the control group. 4 were alive at the end of the study. Of the 69 patients in the treatment group, 24 were alive. And they give us the table here. We have outcome. Okay, and our outcomes are alive and dead. And then we have control, and we have treatment. Now, this is a study. This is an experiment. We have a control group and we have a treatment group. In the control group, at the end, we had 4 alive, and we had, unfortunately, 30 dead. So we had 34 people in our control group. In our treatment group, we had 24 that survived the time that we studied them, and we had 45 that passed, giving us our 69 people in that group. And so we had a total of 28 people who survived and 75 people who passed. And so we had 103 individuals in our study. Okay. Part A says, what proportion of patients in the treatment group and what proportion of patients in the control group died? So we want to know what proportion of patients in the treatment group and what proportion of patients in the control group died, right? That's what they're asking us here. So if we take this, then I'm in Italian. So part A says proportion treatment died, right? That's what they asked us about. So the proportion in the treatment group that died was 45, right? 45 out of 69. Whoa, my pen just blew up. Hold on just a second here. I just made a puddle of ink on the paper. I mean, on the whiteboard. Hang on just a sec. Sorry about that. I think I've got it taken care of here. So we had 45 of the 69. I'm still doing it. I don't know what's going on with my pen. All right, 45 of the 69. Now, I already did this division, but you would have to do this, of course, on your calculator, and you get 0.652 or 65.2%, right? And then they asked us for the proportion in the control group who died. And there, for died in the control group, we have 30, unfortunately, out of 34. And again, I already did this math. This turns out to be 0.882 or 88.2%. Okay, so that's all they asked us from part A. Part A said, what proportion of patients in the treatment group and what proportion of patients in the control group died? And so that's what we have. Part B says, one approach of investigating whether or not the treatment is effective is to use the randomization technique. This is what you and I did with our treatment and placebo example in class. We could use this randomization technique and say to ourselves, remember, when we use the randomization technique, right, part B, when we use the randomization technique, we're assuming, right? We assume H naught is true, i.e., we assume that treatment and control are independent. or the same proportion will die in each group. That's what we're saying. The same proportion will die in each group. Now, we know in ours, right? We know in our group, that's not the case, right? In our group, if we do the math over here, we had 88.2 minus 65.2. It's great. I'm going to retire this green pen. It's just spitting up all over the. All right, so that one's. I don't think I have another. Here's another green pen. We'll try this one. Then maybe it won't make splotches all over. So I apologize for the splotches. When we subtract these, we know 23% more deaths in the control group, right? That's what we see here. 23% more deaths. So when we do the randomization technique, we're going to assume that this difference is zero, that the treatment had no impact, no relationship. It was independent. So the same proportion will die in each group. Even though we know when we observe this, right? When we observe this, that's not what happened. That's our assumption. That's how hypothesis testing works. We always assume the validity of the null hypothesis. So then they give us this paragraph, right? And you need to look at this in your book. I'm not going to write the whole paragraph on the whiteboard here. It would take way too long. So it says the paragraph below describes the setup for such an approach. So we're going to reinvestigate their study, assuming H0 is true. And this is exactly what we did in class. And they just ask us to write in, fill in the blanks. We were to do it, if we were to do it without using statistical software. See, down the road, we're not going to want to have everybody have cards and sit around and duplicate experiments and put things on the whiteboard. We're going to want our software to do this for us, and we'll get there. Fill in the blanks with a number or phrase, whichever is appropriate. We write alive on how many cards, right? Alive on how many cards? Well, if we look over here, alive is going to be 28 cards, right? 28 cards. We're going to write alive on 28 cards, representing patients who were alive at the end of the study. And dead on, well, we're going to write dead on 75 cards. 75 cards. Because we know at the end of this study, we had 28 alive, 75 dead. Now, we don't care what group they're in because we're assuming the group has nothing to do with it. That's our null hypothesis. Treatment and control are independent. We don't care which group they're in. Keep that in mind. Then we shuffle the cards and split them into two groups. One group of size, blank, representing treatment. Well, this is our treatment group right here, right? Treatment here. So we're going to need 69 cards in our treatment pile. And then the other, and we keep reading, representing, and the other group of size, blank, well, that's going to be this right here. That's going to be our control group. We're going to have 34 cards in our control group. We calculate the difference between the proportions of dead cards in the treatment group, right? Dead in the treatment group, like we did here. It won't be 45 this time, right? Because we're running a different scenario. And we calculate the difference between, I'm just reading here, the proportion of dead cards in the treatment group and control groups. Treatment minus control, okay? Treatment minus control, and record this value. We repeat this many times to build a distribution centered at, right? Centered at, well, our distribution is centered at 23%, right? 23%, 0.23. Lastly, we calculate the fractions of simulations where the simulated difference Oh, I'm sorry. Strike what I just, that was stupid. We're assuming no difference, right? So it's going to be a distribution centered at 0%, isn't it? 0%. Because we're assuming, right? We're assuming that we're going to have the same proportion, and because there's no relationship, right? That's our assumption. There's no relationship. So we're going to have the same proportion in this group and this group. So our assumption, the null hypothesis, another way to think about the null hypothesis, we could add it to our list over here. Or we could say the difference in proportions will be 0, right? If they're going to die in each group at the same rate, if the treatment is not going to have an impact, then we're going to net 0. So our distribution is going to be centered at 0. We have no idea why it's going to be bell-shaped. Just got to take my word for it. We'll get to that later in the book. Lastly, we calculate the fractions of the simulations where the simulated differences in the proportions are bigger than our observed difference, right? A single observation based on a sample, and we had 23%, right? 23%. That's what we had. If this fraction is low, we conclude it's unlikely to have observed such an outcome by chance, and the null hypothesis should be rejected. Okay. Now, in your book, here's the page from your book. In your book, they give us for part B. We're still on part B, right? Oh, I skipped in part B, and I apologize for this. I skipped in part B writing down the hypotheses, didn't I? We know what they're going to be. I've said them out loud over and over here, but in part 1 of part B, right? In part 1 of part B, there's a part 1, part 2, part 3. I totally missed part 1, or part I, if you want to use that instead. It says, what are the claims being tested? Use the same and null hypothesis used in the section. Okay, so if we're going to write that down, right? If we're going to write that down, let's go ahead and just make some room here. Let's get this part A out of here. So this is part B, going a little out of order here. So what do they want us to write? They want us to write down the null, right? The null, and that's our independence, right? Our independence model. This is the idea that there's no relationship, no impact, right? So what we have to write it in the context of the problem, and that's very important in statistics. We don't just get to write no relationship between treatment and control. No. We've got to write it. So we say, right, the variables, and what are our variables called, right? We have outcome and we have group. So the variables group and outcome are independent. Right? Outcome and group, right? There's group up here in the table in the book. Outcome and group are independent. They have no relationship. And now what does that mean in the context of our study, right? It means the difference in survival rates we observed were due to chance alone. Now, you don't have to write it verbatim like I write it. You have to communicate, though, this idea, right? And then the alternative hypothesis, H sub A, the alternative model, that's the phrase our book uses, right? Is that the variables group and outcome are not independent. And I understand you want to just write here, it's the opposite of this. You can't do that. Statistics is not like that. We write and we write and we write. So the variables group and outcome are not independent. Okay. The difference in survival rates that we observed was not due to genes, right? The heart transplant treatment is effective. That's what we would write here. Okay. Now back to part 3, right? Back to part 3. When we look at this, right? When we look at this in the book on this page, right? On this page right here. When we take a look at this, and I'll try to, well, I know it's gonna be hard for you to see on the video, but you can always zoom in. 23% is right here. Right? This is 23% right there. 23%. There are only 2 observations that are that are bigger than 23%, right? Because part 3 says, what do the simulation results shown below suggest about the effectiveness of the treatment program? Well, if, right? If, I know I said like 19 times, but it's important. If our null hypothesis is true, we would have expected to get 0 difference. 0 difference. But we got 23% in our one single observation. We got 23%. Now follow along with the logic here. We did it once. We saw 23%. Right? They did a simulation down here, and I don't know how many dots are on this scattered diagram. They didn't tell me up here how many simulations they ran. What do the simulation results shown below suggest about the effectiveness of the transplant program? I'm not going to sit here and count all those dots. Let's say, just for our sake, there's 100 of them. Okay. There are only 2 of those dots over here. 2. There's a dot and a dot. There's only 2. 2 out of 100 is 2%. If, now this is the important part. This is the part you've got to write down. If our null hypothesis were true, if our null hypothesis were true, it's so important. I'm going to write it down. Okay? And I'm going to write it down. If our null hypothesis were true, we would have observed our result of 23% only 2% of the time. Now, what does that mean? It means either something happened that only happens 2% of the time, and we saw it, right? We saw it. We saw it. We saw something only happens 2% of the time in our one study, 2% of the time. Or the assumption upon which we based this entire study is false. Okay. So we either saw something that rarely happens and we're lucky enough to observe it, or the foundational assumption upon which we based this claim is false. We always choose the latter. Okay. So we never conclude we observed a rare event. Okay. We always conclude in this case where this probability is tiny, we always conclude in this case where the probability is tiny that our underlying assumption is false. i.e., we reject H naught in favor of H sub A. And we're going to reject the claim that this treatment has no effect, and we're going to conclude that it does. Right? That's the thought, the science, the logic behind hypothesis testing. Okay? So that's problem 2 in your homework. Now, problem 3, right? Problem 3 is essentially the same as problem 2. So I'm going to leave you to work on problem 3, okay? Because in design, question number 3 is a similar question to question number 2. Now, what about question number 4? Well, we'll work that one out together, okay? We'll work that one out together. So let me erase all of this. I'm going to go ahead and I think we've got the idea, hopefully, behind hypothesis testing down at this point. So I'm going to go ahead and erase all of that, make some room here. I don't know if I'm going to be able to get this on camera for you or not, but for those of you that have trouble staying awake during my statistical lessons, I'll see if I can do this and stay out of the way. You're not alone. I don't know what you can see there. Let me see if I can get out of the way here. So I can get this all the way to where it needs to be. I'll move out of the way. That's I don't want to rearrange the whole camera because then it won't be centered. But what you're seeing there is the tail end of my lab, and she is comatose on the bed. She loves to come up here with me when I make videos in my YouTube studio up here, but she rarely stays awake. So you're not the only one bored by my lessons. I don't know if that makes it any better, but it's just a fact. So let's look at question number 4 now. Sinusitis and antibiotics. Okay, so this is going to have something to do with sinusitis and antibiotics. Researchers studying the effect of antibiotic treatment compared to systematic treatment for acute sinusitis randomly selected 166 adults diagnosed with sinusitis. Randomly assigned, 166 adults diagnosed with sinusitis into 2 groups, as discussed in exercise 1.2. So that's where we saw this the first time. Participants in the antibiotic group received a 10-day course of an antibiotic, and the rest received symptomatic treatments as a placebo, right? They received treatments for their symptoms. You know, you got a stuffy nose, here's some decongestant. These pills had the same taste and packaging as the antibiotic, so we don't have any biases being introduced here. At the end of the 10-day period, patients were asked if they experienced improvement in symptoms since the beginning of the study. The distribution of responses summarized below. Okay, so this is question number 4, right? So what do we've got? We've got, we'll just make a little table here. So these people reported improvement, all right? And we have a yes. Yes, I thought I improved. And we have a no. No, I didn't improve. And then we have our treatment over here, right? Hang on, I'm going to pause the video and take a phone call, and I'll be right back. All right. So remembering back where we left off, not that it's been any time for you, but so I can remind myself, we had reported improvement, yes or no. We had a treatment, and our treatment was we had our antibiotic and we had our placebo. And our numbers were 66 people on the antibiotic reported improvement, 65 people on the placebo reported improvement, 19 people on the antibiotic said no improvement, 16 people on the placebo said no improvement. We had 85 people on the antibiotic, 81 people on the placebo, giving us 166. So this was 131, and this adds up to 35. All right, so there's our table, right? That's our table right there of results. All right. Part A, what type of study is this, right? Is this observational? Is this an experiment? What type of study is this? Well, this is an experiment, right? It's an experiment. How do we know that? Well, we have a treatment group and a control group. So we're impacting our individuals. And since we're impacting our individuals with a treatment, this is an experiment. So we will be able, because we randomly assign them, right? We randomly assign them to two groups. We will be able to talk about causation here because we're running an experiment. Association doesn't get you causation, but in an experiment, you can get causation. Part B, does the study make use of blinding, right? Blinding. So part A, experiment. If I was writing this on a quiz, I wouldn't write just experiment here. I would certainly write out why. Yes, you're not going to get full credit if you write an experiment. You're going to have to substantiate, defend your answer. Part B says, does this study make use of blinding? Now, yes and no, also not a good answer here, right? Yes, by the way, it does make use of blinding because the people given the placebo, right? People given the placebo do not know they're being given systematic dosages of medications that only take care of their symptoms. They're unaware of this. We have doctored that medication up. It's exactly the same in appearance and taste as the antibiotic. Therefore, this experiment does involve blinding, okay? So again, we don't answer yes or no to questions in a statistics class. C. Compute the difference in proportion of patients who self-reported an improvement in the symptoms of the two groups. So they want us to have the proportion in the antibiotic group minus the proportion in the placebo group. Now, our book hasn't really talked about this very much, but P with a hat, that means sample proportion, sample proportion. So it says, compute the difference in the proportions of patients who self-reported an improvement. All right, so improvement is yes. So in the antibiotic group, we had 66, right? 66 out of the 85 minus We had 65 here out of the 81, right? 65 out of the 81. These are the ones that reported an improvement. Now, we need those as percentages, and I already did the arithmetic earlier for this. So this is 0.776 minus 0.802. All right. So the improvement rate, right? The way they've asked us to calculate it, they want antibiotic minus this. So this equals, right? And if we subtract these, this turns out to be 0.026 negative, or negative 2.6%, right? So what does that tell us? Well, that tells us that the improvement rate is 2.6% higher, right? Higher in the placebo group. For all of us who get a sinus infection and run to the doctor to get antibiotics, based on what we're seeing right here, the improvement rate is actually higher in those people who just treated their symptoms with over-the-counter medication by 2.6%. Now, is that based on chance? Is that based on a result that these are independent, i.e., is it based on chance? Or is there a conclusion to be determined about these not being independent, right? That's what hypothesis testing is all about. And the problem's walking us through that, isn't it? Part D says, at first glance, does antibiotic or placebo appear to be more effective for the treatment of sinusitis? Explain your reasoning using appropriate statistics. Well, at first glance, right? At first glance, which one appears to be more effective? Well, at first glance, it would appear, right, based on this number here, that how did they phrase it? At first glance, does antibiotic or placebo appear to be more effective? At first glance, it appears the placebo is more effective, doesn't it? I mean, at first glance, it appears the placebo is more effective, because after all, we have 82.2% saying they improved versus 77.6% saying they improved. So at first glance, it looks at first glance like the placebo is the better treatment. Explain your reasoning using the appropriate statistics. Well, the proportion of people who had the placebo that improved, reported improvement, is higher than the proportion of people who had the antibiotic that reported improvement. What about, so that was part D, right? That was part D. Part E says, there are two competing claims that this study is used to compare. The null hypothesis that the antibiotic has no impact, and the alternative hypothesis that it has an impact, right? Those would be our, this is part E, our null here, right? That's our independent model, right? Our independent model. Our null here is the variables treatment, right? Treatment and improvement, right, are independent. And then the alternative, right, that the alternative model, the variables treatment and improvement are not independent. Now, this is appropriate for this video. This is not appropriate on a test or a quiz. You're going to write everything out. Statistics is about writing everything out. Okay? Write out these two competing claims in easy to understand language and the context of this, of the application. So the null says, right, that the observed difference was based just on chance, The alternative says the observed difference is not based on chance. It's not based on chance alone. Part F. Now here we go, making our conclusion again, right? We've seen this now a few times, how we're going to make our conclusion. We're going to assume, right, our conclusion is always based on the assumption that H naught is true. So we're going to assume there's no difference, i.e. there's no difference in the impact of this. So when we subtract the two, we should get 0, right? We should get 0. So when they get to part F here, though, in this problem, they flip the script, right? This is what we've done up until now. But now they're flipping the script a little bit here. So we have to read this. I'll even change pin codes. We've got to read this carefully, right, to see what they're asking us. It says, below is a histogram of simulation results computed under the null hypothesis. Right, computed under the null. In each simulation, the summary value reported was the number of patients who received antibiotics and self-reported an improvement in symptoms. So this is what they've recorded. Okay? This is what they've recorded. Write a conclusion for the hypothesis test in plain language. Hint, does the value observed in the study, 66, seem unusual in this distribution generated under the null hypothesis? Okay, so here's our picture. All right, I know it's small, but this is our picture. 66 is right here, right? This is 65, 66, 67, 68, 69, 70. 66 is right here. So if we look at 66 on, we have this much. Okay. Does that seem like a rare event? And the answer is no. Right? That's bigger than 50% of the area. That's 50% of what we observed, we could probably observe 50% of the time. Right? 50% of the time. So that's problem number 4. Now, if you're looking at the answers in the book, they don't match the question that we just did. So be careful if you're trying to get the answers in the book to match the question. If you're going to write down the answers in the book, they're not even from this problem. Don't ask me why. I don't have any idea. Okay. Let's see if so we were asked to do 1, 2, 3, right? 4 and 5. Okay. So I will leave you to work on question number 5, right? I'll leave you to work on question number 5. And if you have issues with question number 5, we can talk about it on Monday during class. Right? So I hope this video helps you. If it does, tell your friends in class so they'll watch it as well. This has nothing to do with our video. All right, so everybody have a wonderful day and good luck with your homework.